Hello, so today I'm going to talk about bifurcation diagrams. Now, in order to understand bifurcation diagrams, you already have to understand phase diagrams. I'm going to assume that you do already understand phase diagrams. If you don't, there's another video on that. So let's get started with that. So with a phase diagram, we're going to have just a line, a vertical line. We're going to use to represent the different values of equilibrium and the directions of the differential equation, or the direction of the equation. And we know that because dx over dt is equal to x1 minus x. So that's the equation I think I'll use for this. The entire equation is in terms of the dependent variable. So we know that as t changes, it doesn't change the result. It doesn't change the slope. So we plot some points. We'll find out by solving the differential equation for 0. So we have x equals 0 and then x equals 1. We plot those points here. So x equals 0, x equals 1. We know that all the way across, the slope is 0. And then by plugging in different points up here, so in between the critical points, the critical values, we'll see that the equation goes down, up, and down. So there we go. That's the directions for the equation. With a bifurcation diagram, we take that phase diagram and we just extend it for different points. So I'm going to use the example where y squared minus ay plus 4 equals 0. So that's our differential equation. dy over dx is equal to that. And so when we solve it, when we solve this for 0, we can solve with that a in there, and then we can vary the a and change the result. So solving this differential equation for 0, we get y is equal to a over 2 plus or minus the square root of a squared over 4 minus 4. So we know that when a squared over 4 is less than, or minus 4 is less than 0, there are two equilibrium points. When a squared over 4 minus 4 equals 0, there's going to be one equilibrium point. And if a squared over 4 minus 4 is less than 0, we're going to have 0 equilibrium points. So if we think about it, when this value varies, right, with the a squared over 4 is greater than 0, it's just going to come up with two numbers, right? Because we have the plus or minus. With if it's equal to 0, then the only value that we get for y is going to be this term. And then if it's less than 0, the square root of any negative number is a complex term, so it doesn't result in any solutions. So looking at a phase diagram, we'll see vertical lines like this. So those represent different test points that we can use. And if you were to graph those test points, we'll find that so here's where there's one equilibrium point, there's two equilibrium points, here's two equilibrium points, here is 0 equilibrium points. So different directions we could have. Maybe it goes up and then down and up here. And that can change too, the direction. Maybe it does that. And here it just has direction. There's no other test points. There's no points of equilibrium. And so we can just graph this. And it's sideways parabola. This is what the bifurcation diagram generally looks like. So we can do different test points to see that, or we can solve for this. So if we do another example, if we have the equation dg over dt is equal to g cubed plus c times g. We're going to solve that, so we have g cubed plus cg is equal to 0. So we just want to test, okay, we're going to solve the differential equation. And so we end up with g times g squared plus c equals 0. And so g is equal to 0 is 1 point. The next one is going to be g equals plus or minus the square root of negative c. So if so we know we always have one equilibrium point, which is g equals 0. That doesn't matter. But how many other equilibria are there? Well, if negative c is less than 0, equal to 0, or greater than 0. So these are the three different conditions, like critical points. So if it's less than 0, so if this is a negative number, then there's going to be 0 for this. So plus 1. So we have one equilibrium point. If it's equal to 0, well, then it's still 0, right? That's the same condition. So that's not adding anything. So there's still only one equilibrium point. And then if it's greater than 0, then we have 2 points now. So we have the plus and the minus. So we're going to have 1 plus, or it's going to be 2 plus 1, the original one up here still. So we have 3. So we can either have 1 or 3 equilibria, depending on what the value of c is. You might also see questions where we have like some sort of graph of an equilibrium, a bifurcation diagram, and it's going to ask you, based off of a critical value or a value of c, how many different equilibrium points are there. So you just have to, you can move this c here along the line. So we have it here, there are 0. This is the bifurcation point here. So the bifurcation point is when there's one equilibrium point. And then we can continue to vary it. So c gets varied, right? We start here. We move along the parabola. There's always 2 here, and then you get to the bifurcation point. There's 1, and then there's 0. It could also look the other way around, like that, because it could be a negative c, like our previous example.